In this presentation, we analyze how Google operates its data centers from a sustainability standpoint, the matrices they track, the methods and tools used for measurement, and the strategies for energy optimization. Data centers globally consume large amounts of electricity, and their cooling systems also use water, contributing to carbon emissions and resource depletion. As AI and cloud services expand rapidly, large operators like Google play a critical role in pushing the boundaries of energy efficiency. This makes Google data centers a valuable case study. Google sustainability goals and commitments. Google has set ambitious sustainability goals. They aim operate on 24 by 7 carbon free energy in every grid region by 2030. That is, every hour of every day. They also match 100% of their electricity consumption with renewable energy annually. Though that is matching in aggregate, not always hour by hour. In 2024, despite growth in demand, Google reports it reduced its data center energy emissions by 12%. They also increased their water replenishment efforts. In 2024, they replenished 4.5 billion gallons of water, raising their fresh water replacement ratio significantly. Key sustainability matrices. To analyze sustainability in data centers, we focus on several key matrices. First, power usage effectiveness measures overhead energy versus IT load. Second, renewable clean energy percentage. How much electricity is from clean resources? Third, water usage replacement it is used, water used for cooling, and how much is replenished. Last, carbon emissions, carbon intensity, emissions associated with the operations. We can also include matrices like waste diversion, hardware reuse, and circular economy practices. Matrices power usage effectiveness. We can also see the official links regarding power usage effectiveness as shown in the slide. Power usage effectiveness that is defined as the ratio of total facility energy, cooling, power conversion, lighting, etc. The energy consumed by the IT equipment, servers, storage, network. A perfect PUE of 1.0 means there is no overhead, which is practically impossible. Google's reported fleet-wide PUE in recent years is around 1.09, which means relatively low overhead. Historically, Google has kept PUE greater than 1.112 across its fleet. Since about 2013, by contrast, many enterprise or typical data centers may have PUEs of 1.5 or higher. So, Google efficiency is significantly better. Now, renewable or clean energy matrices. Another important metric is how much of Google's electricity comes from renewable or carbon-free resources. Google matches 100% of its annual electricity consumption through renewable energy purchases like wind, solar, etc. However, matching annual does not guarantee that every hour's power is carbon free. To address that, Google tracks carbon free energy CFE by grid region. In recent years, their global average CFE is about 64%. In 2024 alone, Google procured over 8 GW of new clean energy capacity. Also, a strategic approach is co-locating data centers near clean energy sources or building power generation projects tied to them. Water usage and replacement. Cooling is a major component of a data center's resource use. Many facilities withdraw large quantities of water. Google reports total water withdrawal for their data centers and offices in 2025 as approximately 24 billion liters. That is approximately 6.4 billion gallons. Their replacement 4.5 billion gallons in 2024 to offset their freshwater use. To reduce water use, Google uses alternate cooling strategies such as air cooling, non-potable water, reclaimed wastewater, or seawater cooling in select sites. When selecting site locations, Google evaluates water risk in the watershed and may prefer air cooling if water scarcity is high. Next, carbon emissions intensity. Carbon emissions are tied to how dirty the electricity is on the grid and how efficiently Google operates. Google uses local carbon intensity data, gram per carbon dioxide per kilowatt hour by region. In 2024, Google succeeded in reducing data center energy efficiency by 12%, even though energy consumption grew by 27%, indicating that the new clean energy capacity came online and efficiency improved. Despite that progress, a large fraction of Google's total carbon footprint comes from Scope 3 emissions, that is, supply chain upstream emissions, which are harder to control. Tools, data resources, and methods for analysis. Conduct analysis. These are the tools and source you can use. Google's published environmental sustainability data center reports. This contains the numerical data. Google's officially web pages on their data centers. Clean energy, best practices. If Google offers interactive dashboards or web visualizations, you can use them to view time series. Use spreadsheets to compute PUE, emission intensities, water matrices from raw numbers. Use academic or technical papers, example, on carbon-aware computing workload scheduling for insights and method validation. Google's infrastructure and sustainability blog post often explains strategies in more detail. Walkthrough. How to compute or verify the matrices. Here, how you practically walk through measurements. Uh, from step 1, from reports, collect the numeric values like total data center facility energy, kilowatt hour, IT equipment energy, etc. Step 2, calculate PUE, that is total facility energy divided by IT energy. Compare with Google's Pro reported values. Step 3, from reports or web data. Note how much clean energy, that is wind, solar, was procured or generated. Also get the local carbon intensity for the grid. Step 4, compute emissions equals to energy into carbon intensity. See how much emissions are avoided by clean energy. Step 5, for water, collect water withdrawal and water replenished values. Compute net consumption or replenishment rate. Step 6, the same for multiple years to see their trends. For example, 2022, then 2023, then 2024, and see if the improvements are happening. Energy optimization strategies employed by Google. Google uses multiple advanced strategies to optimize the energy and sustainability. They use AI, ML, predictive control to dynamically control cooling, adjusting fans, wells, and airflow to reduce energy use. Second, carbon aware compute. They delay flexible workload execution to times when the grid is cleaner. Then they co-locate data centers with clean energy generation or transmission nodes. Uh, Locate data center with clean energy generation or transmission nodes, ensuring closer alignment with renewable power. Then the use of efficient cooling technologies, air cooling, uh, air cooling, non-potable water, seawater or reclaimed water for cooling in suitable sites. They continuously upgrade hardware efficiency, improving compute per watt and consolidating workloads. They enter into a long-term power purchase agreements (PPAs) and invest in clean energy projects to ensure the sufficient renewable capacity. Now, even challenges, limitations, and risk. Even with these strategies, there are challenges. Intermittency. Renewable energy supply is variable, and grids may not always allow 24 by 7 clean power. Delay. Building new transmission or power plant takes time. Site constraints. In water scarce regions, using water cooling is harder. Rapid growth. The rising demand of AI and cloud expansion put pressure on energy and power infrastructure. Scope 3 emissions remain harder to control from the supply chain. Methodological uncertainties. Differences in carbon intensity data, boundary definitions, accounting methods can lead to variations in results. Key findings and recommendations. From analysis, we see that Google achieves very efficient PUE is actively reducing energy emissions and making good strides in water replacement. But to fully realize 24 by 7 carbon free energy, more work is needed in clean energy deployment, grid upgrades, and energy storage. Further, emphasis on carbon aware workload scheduling can shift demand to greener hours. They should continue expanding clean energy capacity and partnerships and push for more transparency and better accounting, especially for supply chain scope 3 emissions. Also, exploring longer term innovation like small modular reactors, SMRs, geothermal, or advanced storage could help ensure few power supply. To conclude, we discuss key matrices like PV, renewable energy share, water usage, and carbon emissions, the tools and methods to measure them, and the energy optimization strategies Google uses. Google data centers are among the most efficient in the world and set a benchmark, but a path to full carbon free operation is still under development. Studying such cases is vital as the cloud and AI sector's growth will be heavily influence our global energy and environmental future. Thank you.